Hi, good evening. Welcome to the seventh online tutorial session of the NPTEL course, Polymer Reaction Engineering. So here we'll be discussing some additional questions that will be useful for you in your assignments and your examinations of this NPTEL course. So since it is already time, I think we can start. I don't know why today Sharavin sir is not here. So let us start today's class. So once again. So I'm Rahula. I'm a Prime Minister's Fellow from the Department of Physics, IIT Kharagpur. So I'm handling the online tutorial session for this particular course. So here, as I told you, we'll be discussing few questions that will be particularly useful for you in solving the assignment questions as well as the uh, am, am I audible?
Yes, audible.
Okay, thank you.
Actually, I'm in the office and
Okay,
some BIS audit is going on.
okay,
So anyway, I managed to come out and join the class. Actually, I don't want to miss the class. Yes,
okay.
yes. I'm,
Thank you so much.
yes,
Okay. So yeah, please,
yes.
I won't ask you much question. Please carry your work, and I will just explain you the questions.
Yeah. You can
Okay,
start.
yeah, fine. Okay, so let us start today's class. Yeah, so the first question is, what is the general relationship between the average degree of polymerization, which is denoted as Xn bar, the stoichiometric ratio, or we'll say that stoichiometric imbalance also, and the number of reactor molecules P, or we can also call it as the extent of reaction for a polymerization of bifunctional molecule AA and BB, where BB group is an excess. So typically in the examination, not in the examination, I mean in the lecture, sir has taught basically two kinds of examples, where one BB is excess and one there is another kind of a molecule uh, also. So yeah, and the functional molecule also. So this is for the first case where there is an excess of BB group. So write the equation for general equation, and also write the equation when R is equal to 1 and P is equal to 1. So this is a very typical example, and many questions can be asked from this particular formula. So basically we need to know the relationship between, just a second, let's share answer. Yeah, it's share answer. Good evening, sir. Yeah, okay. So here basically we need the relationship between, just a second. Basically we need the relationship between,
Sorry, good evening. Am I
uh,
audible?
yeah, you are audible, sir.
Sorry. Yeah.
Yeah. So we have just started the class. Yeah. So this is the first question. Here basically we are asked to give a relationship between x and bar, which is the average degree of polymerization, uh, P, which can be said as the extent of polymerization, or also it is like it denotes the number of reacted molecules, and also the stoichiometric ratio or stoichiometric imbalance R. So we need to know the reaction relationship between these three factors, and then what will be the cases when R is equal to 1 and P is equal to 1. So this is the first question. So just think over the answer, then we'll explain. Yeah, so basically we need the relationship between X and bar, P and R. Today's class, I have tried to include many numerical questions because in this part more numerical questions can be asked, and some intuitive questions also definitely. So this was one of the first thing that was taught in this week. So what is the relationship between X and bar, P and R for the case where the one group, which is here in this case, it is BB group, it is in excess. Yeah. So let me discuss the answer. So basically the relationship as follows. So X and bar is related to R and P as such, 1 plus R divided by 1 plus I would just say 1 plus R minus 2P. So this is a basic relationship between X and P and R. So we are asked to, so the first question is to write this relation. The second question is to write the equation when R is equal to 1 and P is equal to, so now we can readily substitute the answer. The first one is when R is equal to 1 it is nothing but xn bar is equal to 2 divided by 2 minus 2p, which can be written as 1 by 1 minus p. The second is when p is equal to 1, so which can be written as xn bar is equal to 1 plus r divided by 1 plus r minus 2, which is 1 plus r by 1 minus r. So these are the two relations that we need for this question. So these are the basic relationship, and from this many questions can be asked. Okay, so if that's the case, let's move on to our next question. So see, this is an application for the previous question. So here we are supposed to find the degree of polymerization. So here the it is said that the conversion rate is 100%, which means that like extent of reaction can be taken as 1. So the complete extent of reaction is it has completed the entire reaction process. So that's the conversion is 100. So the whole reactants have been converted to products and it is of 100%, and it uses AA with 0.98 moles and BB with 1.01 moles. Now we need to get the average degree of polymerization, which is xn bar. Just think over the answer. Again, it is also a very easy question.
Generally, I'm just asking,
Yeah, please.
like if the conversion is 100%,
Huh?
that means P here is equal to 1.
Yeah, yeah, it's p is equal to 1 here. That is the inference that we get from this one.
If the conversion is 50%, then what will be the P?
Then we will take it like 100%, we take it as it's kind of a ratio. So we take it as if it is 50%, we take it as 0.5. We can take p as 0.5. If it is
0.5.
80%, we can take it as 0.8.
Okay, 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 understood.
And thus we can proceed further. So yeah, so let us try to solve this one. So let me write the general formula first. So xn bar is given by 1 plus r by 1 plus r minus 2rp. Okay, so here it says that the conversion rate is 100%, which means that p is can be equated to 1. So it is 1 plus r divided by 1 minus r. This is the formula that we need to know. Now it is said that so to proceed further, we need to know what is r. Okay, so R here is like the stoichiometric ratio. So it is a AA molecule, and it's a like there are two parts for it, and the molecular ratio for A part is given by 0. It's not for AA. The moles of AA in the sense mole of A is 0.98. So basically here there are two moles of A, two molecules of A. So in general here we have to write it as 2 times 0.98 divided by 2 times 1.01. Okay, now if we could solve further, so let me try to solve this. It is 2 times 0.98 divided by 2 times 1.01. So it can be approximated to 0.97. So here R is 0.97. It's like 0.902 something. So it can be approximated to 0.97. Now I can write xn bar as 1 plus 0.97 divided by 1 minus 0.97. So again, then it can be written as 1, just a second, it's 1 plus
60.
0.97,
Yeah,
yeah,
66.
divided by, yeah, 1 minus 0.97. Yeah, it's 65.66. So it can be approximated to 66. So the degree of polymerization for this case is 66. So this is a very similar question that is given in solved by Professor itself. But to have an introduction, we'll start with the same question itself. So the final answer is 66. So as
Uh,
yeah,
yeah, sorry for that. One small
yeah, please,
query.
yeah,
Now, the degree of polymerization earlier equation we have written 1 plus r divided by 1 plus r minus 2p.
uh,
Here we have added one more also, r also, whether like the denominator.
yeah. here we are consider P to be equal to 1. So it is like 1 plus R by 1 plus R minus 2 R. So that is why it's 1 plus R by 1 minus R.
Okay, okay. But earlier equation, just previous question.
Yeah, that is also
Previously.
same.
Okay,
So
but
that,
that is not figuring up.
yeah, so I can explain the previous year question, the previous question. So in this, in the previous question, the first thing it was asked that write this particular formula. What is the relationship between x n bar, R, and P? So this is the equation. And then we were supposed to write equations for two special cases. That is when R equal to 1 and P is equal to 1. When R equal to 1, it will be what, like 2 by 2 minus 2p. So it's basically 1 minus 1 by b. And when p is equal to 1, it is 1 plus r by 1 minus r, which we have seen here.
Okay, clear, clear.
Yeah,
But because last time, because last slide, I think there was this R was missing in the denominator. Uh, Maybe
okay.
that box.
Yeah, this part. Okay, I'm sorry.
Oh, no issue, no issue. It's
Yeah,
just that now it is clear. Now it is clear.
yeah, now it's,
Okay.
so this is the fundamental equation in this paper form. Okay, so yeah, so now let's move further. So now, what are the methods for controlling molecular weight in a linear polymerization? So basically, in the lecture, Sir has described um, three different methods. So what are the those three were called as the three major methods for molecular weight control. So in a linear polymerization. So what are the major methods by which we can control the molecular weight in a linear polymerization reaction? Yeah. So let me discuss the answer now. So the question was, what are the major methods for molecular weight control in a linear polymerization method? So three major methods was discussed. One was quenching. So one was by the first one is one was by quenching the reaction. So when we control the temperature, say we, or in general, if we can say if we can cool down the reaction, then desired molecular weight can be achieved by controlling the temperature of the reaction itself. The rate at which the reaction occurs, or like in general, we can basically control the whole reaction. The first one is by quenching the reaction. The second method for controlling the reaction is by increasing the quantity of one reactant over another. So what happens is that one of the reactant get completely utilized, and then the other one, which is as which is like which is in the surplus, would act as a chain part of the reaction. It will just come and join at the end, and thereby we can basically control the reaction. So one part is by quenching the reaction, the other part is by increasing the quantity of one reactant over another. So the second one is increasing the quantity of one reactant over other. And the last one, which is the other one, is like by by introducing a using a monofunctional monomer monofunctional monomer. So these are the three. When a monofunctional monomer is added, like it will go and attach to a bifunctional monomer, which is there, which will definitely it will like reduce the possible number of reaction, and thereby eventually we can control the whole molecular weight, which is like the molecular. So basically these are the three methods by which we can control the
Yeah.
molecular weight in a linear polymerization. The first one is quenching the reaction. Basically, we control the temperature. The second one is increasing the quantity of one reactant or other. And the third one is by introducing a monofunctional monomer. So by three,
Just one thing.
yeah, please.
Just one thing. Here, the controlling the molecular weight. It means to reach to a dead polymer, like the
Yeah,
saturation level of polymerization.
no,
Means already the polymerization reaction is taking place, and it means the termination of the polymerization.
yeah, kind of yeah, we need to stop the reaction at some particular point and then we can control the weight.
That is what weight control in linear
Yeah,
polymerization
yeah,
is.
yes, definitely. Yeah. We'll we'll like stop the reaction at a particular instant so that we can have the basic like
We
weight.
can say termination. Termination.
Yeah, kind of termination itself. Yeah. Okay. So no, okay. Then it's fine. So let's go on to our next question. Yeah, these are the answers. So the next question is, what are the major disadvantages of controlling the molecular weight by quenching in linear chain polymerization? So we told that there are basically three factors, but controlling the temperature has a major disadvantages. What is that? What is a major disadvantage in controlling the?
Here we are not killing the terminating the reaction. We are
Yeah,
just quenching it. So
yeah,
if there is a chance that temperature goes up further, it can react further. So it
yeah,
is like live.
yeah. Also, we can say that the polymer that
This
is
is not necessarily. It is, we are not terminating the polymerization. This is not
yeah,
necessarily. Not necessarily.
yeah. Basically, yeah, it can lead to like addition of further other functional groups into this because that at
Like
temperature
if
changes, maybe at that particular temperature other reactions can takes place and other minimal functional groups can just add up into the chain and thus that will like a proper controlling of the weight may not be achieved by just uh, changing the uh, changing the temperature.
it may just slow down the reaction.
What?
It may just like to the controlling the molecular weight,
Hmm?
like indicate the slow down the reaction.
Slow down. Also, we can say that the functional groups can undergo other reaction, further reactions also, because we are just basically te reducing the temperature, and maybe that will be favorable for other reactions. And then obviously the functional groups within the polymer can lead to multiple other reactions, and eventually that will give us a very unstable polymer. So there is a chance for such a kind of. It can be viewed from many perspectives, but as per the lecture, from Sir, what Sir has said is like it will eventually lead to further. Yeah, many things can happen because we are basically changing the temperature. So that is one of the major controlling parameter. So changing the temperature can affect in a multiple manner. So yeah, so one of the is that the functional groups within the polymer can undergo further reactions and then that will eventually lead to a very unstable polymer. Okay, fine. So yeah, if that's the case, let's move on to our next question. Yeah. So that to better regulate a polymer's molecular weight, the dash of a bifunctional or monofunctional or monomer must be precisely balanced. So what is that major thing that has to be balanced so that we can regulate a polymer's molecular weight? So we can definitely expect such kind of questions in our assignments. So to better regulate a polymer's molecular weight, the dash of a bifunctional or monofunctional monomers must be precisely balanced.
Amount of
Hello?
Is it amount or like
Yeah,
quantity?
that is very close. This kind of amount, but more specifically, we can call it as the stoichiometric ratio. Stoichiometric.
Uh, can I ask just one simple, like
Yeah,
basic question? Can you
yeah.
explain little bit this stoichiometric ratio? Actually, I could not able to relate and get the exact concept of this particular ratio.
Stoichiometric ratio is basically suppose in a reaction there are A and B. So what is the ratio between this A and B of this particular reaction? So in the previous question we say that suppose there are two reactants, and if the stoichiometric ratio is very, it's not, so suppose we say that the quantity of one reactant is very larger when compared to another, then we can say that the stoichiometric ratio is very higher, or either it can be like depends upon what is divided in the numerator and divider. What is, so it is not a balanced, in general we can say it is not a balanced. So in that, but so that is basically stoichiometric ratio is the kind of like if we say that 2A plus 3B would give you some C. So here the stoichiometric ratio is 2 parts of A and 3 parts of B. So that is the stoichiometric ratio that is involved in this particular reaction. So stoichiometric ratio is like, stoichiometry is like the quantity that quantity of one and the quantity of other. So that what is the quantity of A and what is the quantity of B that we are actually quantity in the set, the ratio of the reactant particles that we are dealing with. So stoichiometry
Wait,
is just a,
just a ratio of
yeah,
quantity of A and quantity of B.
yeah, the what would I say, the reactants that are particles that should be taken in a particular ratio. In that we say that it should be in the particular stoichiometric ratio so that the reaction is possible. Or else if one is, there are reactions, if one is large, very higher than other, it can give some other impurities or it can form some other byproducts in the reaction. So it should be properly controlled, or else if we can see that there are multiple reactions. For example, if we talk in the field of this battery, so there is a one very good material that people generally work on, which is called the NMC material. NMC is nothing but nickel, manganese, and cobalt. So there are also a ratio, particular ratio of this. So people used to work on different kinds of ratio. So there is a ratio like which is 3 is to 3 is to 3, or in general we can call it as 1 is to 1 is to 1 also. So this would give you a certain type of characteristics. Or else we can increase the ratio. In general we take the ratio. So there are other type of ratio which is 60 is to 2 is to 2. So NMC we generally call it NMC either 333 or it's 111, both are same. So or then we call it as NMC 622, or there is NMC 811. So all these contribute to different kinds. So here we are basically talking about the stoichiometric ratio and what ratio we are. So NMC is basically nickel manganese cobalt oxide. So it is basically N nickel NiMnCO2. It's basically a complex thing like this. So yeah. So here also what I mean to say is that here basically we are varying the, so each of them would give you, so when the properties of NMC 333 would be slightly different from that of NMC 62 and that of a NMC 811. Okay. So people work on these kinds of materials. So this same,
Understood.
so this is the basic idea of this stoichiometry. We need to kind of tune the ratios of molecules that we are using in the reaction.
Like 1 is to 1 is to 1, that means equal ratio of
Yeah,
nickel, manganese, cobalt.
yeah. If it is 6 to 2, we take the ratio. So this is, so these are the general configurations that we work on. Yeah, definitely other can also be possible, but in general people tend to move to this. So this is just an example.
Okay, okay. In
Okay.
terms of stoichiometric ratio, but
Yeah,
sometimes we call non-stoichiometric.
not stoichiometric. Sharavan sir, can you help us in this manner? Not stoichiometric.
Here, the stoichiometric ratio, what I understand is we are now talking about the functionality of the monomers. So here, one is like, for example, we are having functional group at both ends, where we will have like control of molecular weight is like it will propagate on both sides. If I am having a chain where I am having the monomer which is having functionality at both ends, say for example diethylene glycol, this is just an example I am referring to. So where are even the acids per se, adipic acid or for nylon. So we have a functional group at both ends. Then if that is the case, then it will allow to what we can say propagate the chain to a maximum extent so that molecular weight will be higher. Whereas when we say monofunctional monomers, that is having functional group at one end. So if the functionality of monofunctional monomers are more, then likely chance that we may not end up with more molecular high molecular weight. It will be getting terminated quickly. When we have bifunctional monomer, then definitely that will be having more what we can say like rather we can have high molecular weight. So that to regulate a polymer molecular weight, the ratio of these two has to be
Precisely
precisely
balanced.
balanced. So that is the point I am trying to get from
Yeah.
this question.
Yeah.
So
So when
because
we say when they get the idea of non-stoichiometry, it basically states that in some we cannot just write as a natural number maybe. So here I told you, for example, in this so he's asking him of a in more general questions. What is the stoichiometric ratio and what's the non-stoichiometric ratio? So what I understand is in the stoichiometric ratio where we can have C in this, we can precisely write in terms of
Some integer
natural
will be
numbers.
there. Yeah,
Yeah. In
some
some
kind
we
of integer
cannot
will be there.
just
Yes,
yeah.
yes, yes. And in non-stoichiometry, there will be no, will not be
Yeah,
integer.
it can be kind of a integer.
Kind of,
So
it will come in a decimal form.
yeah, it cannot be just kind of a symbol in natural numbers like this.
Yes, yes.
Okay. So I think that is a basic difference between these stoichiometric and non-stoichiometric ratios.
yeah, probably I will just give me a time. I will refer and get back to you during the course.
Yeah. Okay.
Okay, okay.
Okay. So let's move on to the next question. So to obtain high degrees of polymerization, higher dash and the acceptable dash are required. So we obtain high degree of polymerization, we need something to be it's higher and the other should be in the acceptable range. So what are they? Can give you a hint because to get into the like domain, like we are basically talking about the conversion and the reaction rate, or I mean the not reaction rate, the stoichiometric ratio R and P. So to obtain high degree of polymerization, which are the two that are um, essential requirements? So which one should be higher and which one should be the acceptable one? So yeah, this is just a logic. Now definitely we can think.
Acceptable free radicals.
Yeah, that's why I told you in which domain we are talking. We are basically concentrating on the conversion and the stoichiometric ratio, the P and R that we talked.
Okay, okay.
Yeah, it should be higher in the conversion, and we should have an acceptable or the other way.
Stoichiometric.
It
Yeah,
is it should be on the higher side, and we should have an acceptable conversion.
no, actually it is on the other side. We should have an acceptable stoichiometric ratio. Metric ratio.
Okay, okay, got it. Because
Yeah,
okay, higher the
the higher
conversion
the
means
ratio.
the higher molecular weight, maximum molecular weight we
Yes,
can,
yes,
and the degree of polymerization we are allowing it to add more monomers to reactor.
yes,
So conversion depends directly on degree of polymerization. Correct. Yeah.
yes. Yeah. Okay. So yeah, these are the answers. So definitely, once again, I'm telling you, you can definitely expect these kinds of questions because these questions are very similar to your examination questions and yeah, assignments questions that will be provided. Okay. Okay. So let me ask you one question. So currently, this week's lectures are going on, right? Actually, I'm not enrolled to that course. So the week
I think
7 is currently undergoing, right?
week 7 is already there, and week 8 also they have loaded.
Okay, okay. So assignment questions have already been uploaded.
Yeah, week 7 tomorrow is the I think day after tomorrow is the last date for week
Oh,
7. Week 8 is also already loaded.
okay, okay, fine. Okay then. So let's move on to our next question. So it is basically the conversions and the stoichiometric ratio.
If it is possible,
Yeah,
in
please.
week 7 assignment,
Huh?
one of the question I'm finding very confusing. Like,
Okay.
uh, matlab, there is a question. If it is like possible, shall I like after
No,
the
what
conclusion
the
of
thing
your
is that we are not supposed to discuss the present week.
okay, okay. Actually, in that question, all the options are like coming. Actually, there is a question mentioning which statement is correct,
Okay.
and all the statements what I was reading
Uh,
is coming. Savan sir would know actually.
okay.
uh, all the
We are not, we
statements
cannot
of
like, since the assignment is going
I
on, it is
completely
not,
understood. That's why I was
yeah,
saying if it is possible.
yeah,
Okay, no issue.
that won't be fair. Okay. So now here also we are asking for a general equation, so which was again discussed in the class. So here a mole of A group is given as Na by 2 and a mole of B group is given as Nb by 2. The mole of a monofunctional B is again given by Nb prime. Then the stoichiometric ratio of the functional group is given by dash. So basically in the class multiple equations was given and we are supposed to, so typical two cases. The first case was the one we discussed earlier where there is excess of bb. Now here is an addition of a monofunctional which is given as b and the number is given by in b dash. Okay, so yeah, this is the question. So this is a very similar example that was told in the class. So we need to have a general equation for r. What is the stoichiometric ratio of these two, of two functional group is given by, basically we need to know a relationship between R, Na, Nb and Nb prime.
It's Na by Nb plus 2 Nb dash.
Yeah, that's the answer. R can be given as Na by Nb plus 2 Nb dash. This is the relation, and I think the next question I put a similar example for this. We need to solve for this question. So definitely we can try that question, then we'll get a fairly good idea. Okay, so that's the formula. So see this question. Find the average degree of polymerization with number of molecules of A and B are given as 1 mole and the number of molecules of monofunctional functional group RB is given as 0.5 when 100% conversion is occurred. Okay, here also we can take P is equal to 1. So here again the conversion rate is, so as we told you, when if it is not 100%, then we will take the value accordingly. If it is like 80%, we can take it as 0.8. That's it. So this is to make the question much more easier. We generally go for 100% conversion. So here number of moles of A and B is given by basically NB prime is given as 0.5. So definitely this is a very easy question. So let me try to solve. So I can write R as the formula is Na by Na plus, I mean Nb plus 2 Nb prime. So it is like 1 by 1 plus 2 into 0.5. So it is like 1 by 1 plus 1. It is 1 by 2.5. And in the question it is given like 100% conversion, hence I can write xn bar is equal to 1 plus r by 1 plus r minus 2p. So when p is equal to 1, it is 1 plus r by xn bar is equal to 1 plus r by 1 minus r. It is nothing by 1 plus 0.5 by 1 minus 0.5. It is like 1.5 by 0.5. It's
3.
0. That's it. So this is just to demonstrate that formula. The question can be formulated in this fashion. So when they change the values of, so basically it is for in these all these cases we take generally the A and B to be equals. So we, these equations are generally we take equimolar conditions where A and B are similar. So that's why in this question also we took both as, yeah, if they are different then we can definitely put the values accordingly and then do the question. So excuse me. Yeah. Okay, so let's move on to our next question. So dash is a combination of polymer molecules of varying molecular weight. So this is a very general question. So yeah. So so what is a what? So yeah, dash is a combination of polymer molecules of varying molecular weight. Again, in the examination, mostly these kinds of questions will have multiple choices, so it will be much more easier to point out where they are actually meaning. So now this question seems can have multiple options, like many things can actually come here. So yeah, it can be looked in different perspectives.
One is like if you are seeing in terms of molecular weight distribution, that is one part.
Yeah,
And
that's
whether we are referring to molecular weight distribution.
hmm. So, but again, this question I add this particular question because this was one of the straightforward question which sir was like he was just stressing on this particularly. That's why I put this particular question. So basically, it is polymerization itself. So this is
Okay, okay.
Or step polymerization or chain polymerization.
yeah, in general we can call it just a polymerization. Yeah. So polymerization is a that is also one of one way of to define polymerization. So polymerization basically it is a combination of polymer molecules that can have multiple molecular weights, or it can have varying molecular weights. Okay. So yeah, let's try to move on to our next question. So, what are the major disadvantages in using chain length as a descriptor in comparing polymers? What is the best descriptor there? So, so yeah, again we are going to fundamentals like in order to describe a polymer, one way is to say about its chain length. But when we go further, so we like initially we were used to talk that we used to tell that polymer like we will just write in a square bracket at the end we'll write n and just then we'll denote a polymer or we just characterize a polymer with the length of its chains. But practically using chain is not that much advisable because of a particular reason. And if that is the case, then what is the other best descriptor we can use to describe a polymer? Not just naming, but in order to compare or say it in a general manner.
Are we looking for PDL, polydispersity index?
What's that?
Or whether we are like one is the chain length when you are referring to
Yeah.
uh, the major disadvantage of using chain length as descriptor in comparing a polymer.
Hmm.
Okay, so when we compare a polymer, maybe the longer chains and shorter chains.
Yeah.
One way is like we can define in terms of molecular weight. That is one part.
Yeah.
Different types of polymer will carry different molecular weight. That is one way.
Hmm.
The way it gets polymerized. And another way is with respect to their functionality.
Hmm.
And in terms of molecular weight, if I am telling, I can refer in terms of polydispersity index also, like PDA.
Yes. Yes. Yeah. Hello.
Yeah, I'm just thinking any one of these will be the best option
Yeah.
rather than simply putting it as a chain length. Like
Yes.
chain length, as you told, we can represent in terms of equation with that. But when we compare between two polymers, either of similar type, only I'm talking about similar type,
Hmm.
then molecular weight distribution or polydispersity index is one easy way we can
Yeah.
describe.
That's it. But the major disadvantage of using chain length is that in practically, if you talk, we are talking about like huge number of molecules. So the previous question we are talking about 1 mole of molecules. So definitely in 1 mole of molecule, like there are 10 raised to 23 number of molecules. So that is a huge number. So just counting, we cannot just directly count the chain in a practical case and then describe it. Because that is much more difficult to process in a practical manner. So the other better way is like we can use this molecular weight to describe. So yeah, so that is basically the difference. If we are just depending on the chain length, it would be very hard to tell because we are talking about a huge number of molecules. But so it is better to describe it molecular weight. Okay, so suppose
Molecular
we
weight
have
is the answer.
molecular weight. So major disadvantage is the number of molecules that we are dealing with is very large, so it is not that much advisable. So the other one of the best descriptor is the molecular weight. So instead of talking about number of, it is the same in basic chemistry also. There also we do not just talk about number of molecules in necessary. We generally talk about the molecular weight that we are dealing with. So we
Pretty
take,
difficult to like
yeah,
measure or to obtain the exact
yeah.
number, like
We say
how
like we
much.
have a 1 molar solution of H2SO4. So if 1 molar solution, or that is a basic, that is a like much more easier way to talk. Similar in the
Exactly.
case of polymer also. The line part is very difficult to comprehend, but we can definitely talk about the molecular weight. Okay. Yeah, the answer to this one is molecular weight. So what is the unit of molecular weight in a polymer? I know this is a very fundamental question, but still to get into one way, what is the unit of molecular weight in polymers?
Mole per
Hmm? Any idea? Yeah. So the molecular weight is very similar to in organic chemistry also we choose the general same way. We generally talk about gram per mole and or we can also talk consider Dalton, which is denoted as degree. These two are the general unit that we talk. So this is in the SI unit. So yeah. So these two are the general units that we talk. Okay. Yeah, more on that and yeah. So now let's try to calculate the weight of this particular monomer and what will be the weight when the degree of polymerization is 1000. So here we are given a monomer. Okay. And now what if the degree of polymerization is 1000? Again, these are very easier question, but to just make the basics clear, you can stick into this. What is the molecular weight of this monomer and what will be its molecular weight when the degree of polymerization is 1000?
So when we are referring to monomer, this is an ethylene. So we are directly asking what is the molecular weight of ethylene.
Yes, definitely. It is very easy, so let me try. We know the molecular weight of carbon is 12 gram per mole.
where xn equals to 1000.
Yeah, and we know molecular weight of hydrogen it's 1, so it is basically 1 into 4
The
plus 2 into 12, it's 4 plus 24, that's 28. And now we are talking about a degree of polymerization of 1000. So basically, we can so there will be multiple other factors. And basically, we can just talk in terms of that are xn is 1000. So basically, there are 1000 such molecules. So it is basically 28,000. Okay. Yeah,
yeah,
this is
yeah.
yeah, this is a very easy question, and yeah, this is just to brush up our basics. Okay, okay, then fine. So let's move to our next question.
We are simply multiplying the
Yeah,
weight we got.
yeah. We have for one monomer it's 28, and we say that the degree of polymerization is 1000, which means there are 20,000 such monomers packed together. So basically, we just multiplied 1000 by 28, it's like 28,000 gram per mole is the molecular weight of the that polymer with polymerization of 1000. Okay. Okay, so in this question, what are the two general distributions of a polymer weight? So there are two kinds of way we generally talk about the polymer distributions in the polymer molecular weight. Say, I mean the polymer weight, and what are these two?
Average and weight average.
What?
Number average molecular weight and weight average
Yeah,
molecular
there
weight.
we are actually talking about the, here we are generally talking about the general distributions in a polymer weight. There are two kinds of distribution that is the number average and the molecular average. So yeah, that is. So here
In
basically we are talking about two kinds of distributions can be possible. So what are the two distributions?
okay, generally it will be one, either it will be narrow or
Yeah,
broad.
that's it. That is so the terms that which I gave for this the mono, disperse, molecular weight, and polydisperse. Disperse. So it's mono disperse and polydisperse. In mono disperse, I'm sorry. So so you have to write like this. So, so in mono disperse, in the x-axis, we can have molecular weight or we can have the number. Anything is possible, and the other one is like number of molecules, basically. Number of molecules, number of total number of molecules, etc. So for the monodisperse case, we'll have a sharp peak. So it says that mostly all the polymers uh, uh, in the monomer, I mean the whole distribution of polymer is basically made of polymers with similar weight. The molecular weight will be like similar. Either I can draw it in much more way. It should be sharper. Okay, so this is for monodisperse. So this shows a monodisperse case, and for a polydisperse case, this will be a much broader peak. Okay, it says that the polymers within are made of multiple molecular weights. There are so basically the polymerization has happened with polymers out with a wide range of molecular weight. It is not just made of one single type of polymer, but it is made of a polymerization has happened between polymers of a wide range of molecular weight. So this is the basic two distribution. This is for poly. We can basically tell this with the width. Here for poly disperse, the width will be much larger. For mono, it will be smaller. So this is a very fundamental kind of classification. Okay, yeah, that's it. This is
Clear.
what, yeah. Okay then. So now we have to talk about what is this number average molecular weight and weight average molecular weight. So there are two factors or two kinds of averaging that we talk about. One is the number average molecular weight and the other one is the molecular average, weight average. So what are these two? Okay, it requires a tiny bit of explanation. So let me explain this one. So as we've seen in the last question, so basically we plot with either molecular weight on the x-axis or number on the x-axis with fraction of total change. We can call it a fraction of total change or number of molecules on the. So basically, it's a number of molecules on the left axis. Suppose we are getting a plot like this. So there's a particular distribution like this. So basically, definitely we can group it into different bins. Okay, we can group it into different bins, and there is a very basic. So here we can basically talk in terms. One way is to talk is like we can say like with a there are n number of atom with a number of molecules with a particular molecular weight. That is one way of talking. Okay, so here we can club the number of, so here it is basically the number of polymers. So say there are 10 number of molecules that yeah, it is a number of molecules in. So basically it is like I can write it as, it is generally denoted as mn bar. Mn can be basically written as summation or I number of molecules, that's the total number of molecules of multiplied by the total number of molecules with weight mi, molecular mass molecule with Mi into that particular mass. Basically, we are talking about the weight itself. Okay, so it is divided by total number of molecules. Number, this is the total number of molecules. See here the denominator is basically we are talking in terms of number. So we have a weight distribution per number. So how many number of molecules are can be put it into one bin? We are having different bins in this one. So basically we talk in terms of number. Okay, so basically we tell that see there are 10 number of molecules with this particular weight, there are 20 number of molecules with this particular weight. In that way, we can talk about an average. So in general, we can write it as summation of Ni Mi by summation of Ni. So it is the number average molecular weight distribution. The other one is the weight average. Weight average, again, we are talking in terms of weight. So what are the weight of the molecules that are arranged? So here we
One is number and another is weight.
weight. Yeah. So here we in the other one, the x-axis, we generally talk about the molecular weight. Here we had the number. Here we have the molecular weight and the number of, sorry, just a second. Yeah. And here we have number of molecules. Okay. Number of molecules. So again, it will have some kind of distribution. If we again club it into different bins, we can say that a particular weight or molecular weight has this much number. Okay, that's it. So this is another way of telling. So here basically we can write m w bar as weight of molecule. So here basically the major difference comes from the denominator part itself, and the numerator we are talking about in terms of weight. So it's yeah, numerator. Here it's number of molecules. So here I can write this as summation Wi, that is the weight of ith molecule, into number of I molecules, number that divided by total weight, divided by summation Wi. So this is a basic definition for this one. And again I can write, if I want, I can write Wi as Ni Mi, because weight, there are Ni number of molecules with Mi molecular weight. So again I can write it in terms of this, and again it can be further reduced to Mi square Mi by summation Mi. These are the two kinds of distribution we generally use. So one is the number average, where we generally talk in terms of number of molecules itself. Where it is the weight average molecular weight, where we actually talk about the weight of the molecule. So these two are very important, because as Sharwan sir told, one of the basic descriptor that we use to define a molecule or a polymer was its molecular chain length. Then we told that other way, better way is to do by its molecular weight. Initially it was chain length, then we told molecular weight is one of the best. The other one where we can generally define a polymer is its which we will discuss in the next question. It is the polydispersity index, PI.
Rahulji, one small
Yeah,
clarification.
please. Yeah, please.
The previous slide, that number average is correct. As a equation,
Yeah,
sigma ni by ni mi by mi.
yeah.
Whereas weight average, I have a doubt that whether it is sigma ni square mi square divided by sigma ni mi.
No, I think this one is correct itself. Because
Okay,
weight for W, I'm writing it as NiMi.
I got it. I got
Yeah,
it.
then I'm
But
multiplying it with Ni, and that's
okay.
why I get Ni square.
Okay, fine, fine. But okay, I had a doubt that whether it should be, because it was like for GPC,
Uh-huh.
we get this both MW and MN.
Okay.
Uh, that will directly give the polydispersity index by measuring this MW and MN.
Okay.
Whereas in vapor pressure osmometry, generally we go with this number average only. That is the colligative property we directly get.
Okay.
So that's why I had a doubt.
Yeah,
Here,
but yeah, but for this one, I have referred this one, but yeah, I think this is correct for this one. I don't know what
okay.
not aware of what you're talking about, but
No issue,
yeah.
no issue. Because I just add a clarification from my side. No, if it is
Okay.
clear, then go. Please go.
Yeah. Thank you. Thank you. So now we are talking about this polydispersity index. So what is a polydispersity index and what are the typical values of polydispersity index? So again, yeah, since we have already learned about the previous, so this is just a continuation of the previous question itself. So as I sir told, like we generate we use this polydispersity index as one of the uh, way to describe the polymer itself. So yeah, so we told that we can describe a polymer by its molecular weight, or in more sophisticatedly, we can tell that this is not just the molecular weight, like we are talking about the molecular weight distribution. So suppose, so molecular dispersity index is basically, it will give you how dispersed it is. So suppose we had two cases. So we had two cases, one has a very narrow width and the other has a more wider width. So the narrow width one is called the monodispersive, and the wider width is called the polydispersive. So basically in the monodispersive is also defined as the one which have the polydispersive index pi to be 1, and the
Sorry to interrupt.
yeah, please.
Just to confirm,
Yeah.
because I just referred one of the book.
Ah,
Probably earlier question, there is a small change.
okay.
Can you just go back?
Yeah,
Just
sure.
with
Sure,
one of
sure.
the
Okay.
here MW stands for like sigma WI into MI. So
Okay.
it will be MI is getting squared,
Yeah.
and this number is 1. NI MI
Okay,
square,
okay, okay. Yeah, that's very true. Yeah, it's
weight into molecular weight.
weight into molar. I think it's weight into mi.
Yeah, weight into MI.
Weight into mi. It's not weight into. Okay. Yeah,
Yeah,
it's
weight
okay.
into MI. So then
Yeah.
it will be, when we are adding the other equation, then it will be NI is there, MI
Yeah.
square. NI
Yes,
MI
yes,
square.
yes, yes. Sorry. I'm sorry. I'm really sorry. I made a mistake here. So it's mi square times mi. Yeah, thank you, sir. Thank you for pointing it out. So yeah,
Uh,
actually it is
yeah.
yeah. Yeah, yes, yes. I'm sorry I made a mistake.
No,
Yeah.
no, just want to clarify because. Okay, please go ahead.
Okay, okay. Okay. So now let's move. So in the previous year question, we were talking about the polydispersive index. So yeah, so here the connection between this question is these two questions are that the polydispersity index can be um, the polydispersity index PI can be defined as the ratio between the molecular weight distribution, like the weight average molecular weight and the number average molecular weight. Weight average molecular weight and number average molecular weight. So the ratio between these two is given as our PI, which is the polydispersive index. And in general, for monodispersive dispersive polymers, we take the value of PI will be 1, and for polydispersive, it will be greater than 1. So in general, it will be in the range of 0.5, 1.5 to 2. So that is the range we generally see this polydispersive material. And when it is so monodispersive, it is a very typical case. It might be very hard to find such kind of materials in the nature itself, because definitely it is very hard to isolate one particular polymer. And the much more common thing that we may observe is the polydispersive of polymers. Okay.
What is the significance of this PI? Why we are like concerned about this
Because it
finding?
says that
Yes.
suppose we have a polymer. You're right. So polymer. So the definition we saw in today's class for polymer is like in polymer it consists of polymerization is a process where polymers of different molecular weights will come and join. So we can say that in a polymer can be a combination of different sub in general we can say monomers of different sizes. Suppose we have a bulk system, and if it is made up of a single polymer, then we can have such kind of a distribution. Okay, the majority of the polymers in the system will have same molecular weight. But
Second kind of.
yeah, but in that is a very typical case, and much more broader one is like we cannot just directly fix the molecular weight. It is very hard to like pinpoint the molecular weight of a, but it will rather be in a dispersed manner. It is like the if you take one polymer and suppose there are n can be the polymerization. So it will be basically a distribution, and that distribution would be a wider one that is more uh, observable than a peak, which one has a peak one. Okay, so this is one. So this is basically, so we need to classify this polymers. So one way is like we just talk about the length. The other way is, the other general way is we talk about the molecular weight. In much more sophisticated manner, we can just talk about the distribution of the molecular weight. So that distribution can have two forms in general. One is a sharp form, one is a wider form. The sharper one have the polymers with equal or similar molecular weight, whereas the wider one has a wide range of molecular weights associated. So this is kind of a way we can generally classify the polymer itself. Okay.
Okay, shall I add some
Yeah,
point on
please,
this?
sir. Please.
Yeah, like practically when we see for a polymer, when we say mono disperse in the sense in the GPC peak, we are seeing the peak is very narrow, which shows that almost all the chains, whatever it is formed,
Mm,
of almost equal length. So practically, when we see any free radical polymerization, I
mm,
am having a monomer, and initially I am trying to give an initiator by either mostly homolytic scission. So once you generate this free radical, the free radical will start to initiate all the monomers whatever available, or wherever, like it will be like multiple chains will start initiating together. So when we see some chains will propagate fast and some chain will propagate slow. So the chain which propagates fast will end up in a bigger chain, whereas the chain which propagates slow will end up in a smaller chain once it gets terminated. So when we see free radical polymerization, you will have a very big chain also, say somewhere close to 1 lakh molecular weight, and something will be in say thousands, 10,000 to 20,000 range. Something will be in 1,000 or less than 1,000 also. So like it is like a distribution of molecular weight is very broad when I say when I go with free radical initiated polymers, which means again here again the point is that I am initiating all the monomers together, but some will proceed first because of the availability of monomer. Some will go fast, some will go less. But generally, when we put that in a GPC, we will see that this broad distribution for the free radical initiated polymers. Generally, anionic or cationic, that is some specific polymerization currently, where we can go close to one, but definitely it will not be one. Any polymer chain getting this narrow chain is really tough, but still we can take it close to one. So practically both will have different applications. So when I say polydispersed polymers, there specifically if I am looking for a control of a property, I am converting this polymer into say some composite matrix in which I will add some fillers and convert it into a composite. So polydispersed polymers, I can tailor these properties to my requirement. So it will give me the flexibility where I can tailor the properties. Whereas monodispersed polymers generally it will be fixed, like molecular weight or monodispersity. Since it is fixed, I cannot play too much on this. So composite related aspects when I am working on end application, polydispersity will be the most ideal one where I can play with the fillers added to that. And monodispersed will have its own application, but that is specific. I know I want to end up in some specific property, then monodispersity will end up. Polydispersity means I can play with the additional inputs added to that so that I can have a broader control over the final end products of this polymer what I am getting.
okay, sir. Thank you, sir. This was also new to me also. Yeah. So GPC is like basically gel polymer chromatography.
No, this is a gel permeation
Gel
chromatography.
permeation chromatography.
So there we will have this again there it is like a polystyrene beads
Mm-hmm.
with an element. So when you dissolve this polymer,
It will
this
like
broad peak, yeah, as the peaks we are seeing, na,
Ah,
So the higher molecular weight chains will come out first, then followed by the low molecular weight chains.
okay.
So the here also actually we are having this curve. It may not be sometimes a single peak. You
Yes,
may get
maybe.
some different peaks. Some
Okay.
initially it will start with small lump, then a bigger lump, something like
Okay. Okay. Okay.
that. So depends. But vapor pressure osmometry is one more technique where we can measure the molecular weight, but that will give only the number average. But that will be the more realistic value than what we are getting from GPC.
Okay. Okay. Fine. Thank you, sir. Thank you so much. Okay. Then I think like time is also going. So let's move on to our next question. So the question is, what are the steps involved in a radical chain polymerization? Yeah. I think we need to go a bit faster. So Sharon sir will definitely can give me an insight into this question also. So basically, the steps can have it will be
Initiation, propagation, and this one
yeah.
termination.
So here we basically have a reactive species that will be act as initiator, and it will initiate the polymerization. Then depending upon the reaction involved, this reactive species will attaches to a monomer and then opening a pi bond. So it will like start bonding, and there it will come. It can be a radical, it can be a cation, or it can be an anion. Then the reaction will be repeated and many more monomers will be added successively, and some stage it will be terminated. So it is basically what we learned in the first class itself. It is basically the initiation, propagation, and termination, and at some point it will be terminated. So these are the basically for the steps involved in a radical change polymerization. Okay.
Like we were talking about radical chain or chain polymerization,
Yeah.
individual one monomer will get joined with the chain of polymerization,
Yes.
yeah, and this individual reaction takes place by adding one monomer at a time.
Yes. Chain, it can be one monomer. It will keep on adding at the end one one. It feels like we have seen the branched one also. So in branched one, like a
Eh,
branch, entire branch will come and join.
yeah, but in chain polymerization, I think it will be just monomer
Yeah,
at a time,
yeah,
and it will keep on adding, and it is getting long and long.
yes. That's it. We have two. We have step chain polymerization and branch
Yeah,
chain
in step
polymerization.
chain, and it randomly like there is a bunch of polymer getting added with the another bunch of polymer
Yes, that's it.
in
One will
when it in terms of step chain, right?
yes.
So
Okay.
the molecular weight will be uniform in the case of chain polymerization.
Uniform in the sense I didn't
Uniform
get
means
you.
every time, suppose there is a reaction taking
Huh?
place with the chain of polymerization, with the backbone of the polymerization, one monomer is added in first reaction.
Yeah. So
Again,
you if you
in
see if you say like if you watch the reaction in some say time t, so is
yeah,
it proportional to t, like the weight is proportional to t? So you're asking like that. Suppose,
yeah.
yeah, if in one
The
second one
rate at
molar,
which the molecular weight will increase, it will be uniform. What I meant to say.
theoretically
Like,
I
am I correct?
think, but I don't know if there is any particular thing practically if we follow such kind of a thing. Yeah, I can't directly comment on that.
Because there is a chances there are both ends, so monomer can add. No, it will be added in one end only because radical is taking place.
Hmm.
Then definitely in one end only one monomer will get reacted and get polymerized.
Yes,
After that, it get polymerized again. That radical species is generated from the main chain only,
yes,
and it get polymerized with the another monomer. So I
yes.
think this uniform rate will takes place. The molecular weight will be get uniform in every polymerization.
Yes, I think we can agree to that. Logically speaking, that is possible, but I don't know if there are um, any some like there are other things also we need to consider. So in a very
Uh,
preliminary logic that is working, but I'm not exactly sure that is the case.
In general terms, I'm just
Yeah, in
saying,
general
like,
terms, that
if,
is very good.
uh,
But maybe there are other factors that might be influencing. So I cannot tell you in a generic manner. But yeah, from a very basic idea, that is possible.
what is the call on this from Saravanan sir?
What do you think, sir?
Yeah, generally for radical chain polymerization, though the terminology says that one after another only this monomer is added, but in practical situation, if we see, the monomers are initiated in parallel. Like we are not restricting some concentration of monomer is available, and I am trying to initiate. So I know how much initiator is required for this monomer to get initiated. Generally all the free radicals whatever I am creating initially will not be available straight away for this to initiate. Sometimes they may again recombine and last also. So generally the efficiency of the initiator is more important, but when it happens it will initiate at a given time as multiple monomers. Like there will be monomers initiating multiple, and some monomers will add more additional monomers, so the, some will go fast, some will go slow. Whereas in step growth polymerization, something like our phenol formaldehyde reaction where we do initially, it is like we convert this phenol with one addition of formaldehyde, it will form one more like monofunctional penal. Like it will form, then next step it will go to bifunctional OH will be added in one more step. Like it is like oligomers, we call it as oligomers. So like multiple oligomers will form first, then only the condensation of that oligomers will happen at a time at the end of the reaction to convert it into I molecular weight. So initially it will be like oligomers only which is forming at multiple steps. So straight away the molecular weight buildup will not be fast in terms of step. So only at the end of the reaction where this all these oligomers condense to remove water, then sudden jump in molecular weight will happen. Whereas in the radical chain polymerization, it is like constant increase. We can see that is the
Exactly,
difference.
exactly. Yes, yes.
Okay, sir. Okay, then I think we can go on to our next question. The delocalization of electrons within a molecule is called dash. So this is a specific term that we have discussed. Yeah. So the delocalization of electrons within a molecule.
Resonance or
Yeah.
resonance.
Yeah, it is resonance. Definitely. That is resonance. Okay. So resonance dash the stability of a molecule. It increases, it decreases, it does not affect the stability, and it is none of the above. So which one do you think it is the answer?
That should increase only because benzene, the stability of the molecule comes from resonance stabilization.
Yes. Basically, resonance increases the stability. Increases the stability of the molecule. Okay. What are different types of conjugate systems? Okay. So this is also very generic question. So there are different kinds of conjugate systems, and so what are the different kinds of conjugate? Because in order to resonance to happen in a system, there should be this conjugate system within that should be possible. That should be there. So yeah, one is like what is a conjugate system? So I think that has already been explained in the class. So like if suppose we have a like there are like suppose we have a B C D kind of an arrangement where we have a similar kind of arrangement between A B C. So this is a similar case. So we can basically A and C are conjugate pairs, and B and C and B and D can be considered as conjugate. Yeah, we can talk in further like we once we deal with this. So what are different types of conjugate systems in general? So this is a very general question.
We referring to this biconjugations.
Yeah, definitely. Pi conjugation.
One is through pi conjugation, another one likely through lone pair electrons.
Yes. Yeah. So let me try to explain this. So there are basically four types of conjugation. The first one is pi conjugation. So in pi conjugation, there will be it is basically there will be this conjugation of these pi bonds associated. Suppose we have four molecules, one, two, three, 4. So in case of pi-pi conjugation, there will be pi-pi bonds in this particular manner. So it will be arranged like in a like one of sequential, like one after another. So this kind of a particular arrangement is a pi-pi conjugation. And the next one is pi cation conjugation. In pi cation conjugation, it is like you have 1, 2, and 3. So here it will be a pi bond, and here in terms of 3, it will be a cation. And similarly, the other one is pi anion conjugation, and here it is like here it is like one side it is pi, so we have 1, 2, and the other side it's a anion. Fourth one is pi lone pair conjugation. Here one end it is a pi bond, the other end it is a lone pair. Lone pair is like basically the electrons that are not participating in the reaction. So typically as an example can be given as H2. Here this is the lone pair electron. So these are the 4 kinds of conjugate systems. Okay. Okay, then I think it is time is also going. So let's move on to our next question. So the termination of an ionic chain polymerization can be processed through dash. I think now the questions are coming from the previous year questions. So like this time I try to club them together so that we can have a better understanding. So yeah, this is from a previous year question. So we can expect definitely questions like this. The question is, termination in ionic chain polymerization can be through recombination of counterions, forming a sterically hindered ion having a very broad chain distribution, forming a sterically hindered ion having a very narrow chain distribution. No.
Recombination with the counter ions. Generally, the other one is free radical. It is like termination by combination disproportion, and multiple ways are there. Here, generally, we need a counter ion where this can be neutralized.
Hmm. Okay.
Recombination of counter ions.
Yeah. Actually, there are two answers are correct in this. First one and the second one. Forming a sterically hindered ion having a very broad charge distribution. So these two can act as a termination to a ionic chain polymerization. Okay. So here we have two statements. The first statement says that the free radical species formation occurred through homolytic cleavage. The second one is the number of free radical species present in the system would always be high to propagate the radical change polymerization.
Yeah, first one I believe it is correct because homolytic scission only generally gives free radical.
Yes.
Second one, number of free radical species should always be high to propagate because radical chain once we initiate the chain itself will have the free radical at the ends to propagate.
Yes.
So the second one I have a doubt whether
Yeah.
it's
Second one
correct.
is like it is not the
False.
case of yeah, it's a false statement. So it definitely as I said the homolytic cleavages are basic for this free radical formation. So that is very much true. And hence, yeah, the options are like first one is true and the second statement is false.
It is not necessarily should be high, right?
Yeah, it is not
For the
because
second,
as I said that
second,
that will obviously that will form that will be a part of this. So it need not be high. So that particular statement,
a small
uh,
amount may takes
yeah,
place
that
this free
yeah,
radical polymerization. Yeah.
yes, yes. So, following are the characteristics of chain growth polymers. Formation of high molecular weight polymers from unsaturated monomers. Formation of polymer from bifunctional or multifunctional monomers. Required initiator to start the reaction. Shows practically no termination step. The polymer weight is largely unchanged, though the average percentage of conversion of monomer to polymer increases within the time of reaction. So there are multiple. So which of the following characteristics are? So some may not be the characteristics. So which are the characteristics?
Yeah, first one it is likely because unsaturated monomers are required.
Yes.
Created. Then the second one also formation of polymer from bifunctional. Yeah, both sides functional group is okay.
No,
Bifunctional.
there it's there is a cast. You said
Yeah,
it's
yes.
bifunctional group.
Yeah, bifunctional means that is the other step growth also will come into
Yes.
the picture there. So the required initiator definitely that is required,
Yes.
but D is not there. It will terminate
Yeah, it
definitely.
will terminate definitely.
Polymer weight is largely unchanged through the average. Yeah, that is last also will be correct.
Yes. So better we can say that the which are not the characteristics of change polymers can be basically this one, the formation of polymer from bifunctional multifunctional polymers. Okay, so that is not a proper definition for this. So as I said, for the bifunctional, it basically comes with a step growth, and definitely it shows practically no termination. That is also the long statement. So the characteristics of chain growth polymers is the formation of high molecular weight polymer from unsaturated. Yes, that's the correct answer. It definitely requires a initiator and molecular weight of largely unchanged, and that is also the correct statement. So yeah, today we are getting a bit late. It's already 1:25. Okay. So here the first statement is ionic polymerization is monomer selective. That is, specific type of monomer can be polymerized through a kind of specific kind of ions depending upon the resonance characteristic induced with specific functional group. The statement 2 state that radical polymerization can usually be used to polymerize most of the addition polymerization species. So which one is correct?
The first one is definitely because all monomers cannot be initiated through or we cannot process through ionic polymerization. There are certain limitations. Whereas a radical can be used to polymerize most of the addition polymerization species. Okay, if I can add like
Yes,
ethylene to a
that's
polymer, that is possible.
yeah,
Yeah,
yeah.
both are likely.
Both
Both
are
are
correct.
correct.
Yeah, both are correct. That's it. The statement 1 and 2 is correct. So, okay, okay, fine. So let's go to the other question. During ionic polymerization, the polarity of the solvent affects the polymerization reaction, and hence, preferably, the polarity of the solvent should be low polarity, moderate polarity, high polarity. Water should be added to increase the polarity.
Definitely, water should not be there. That will
Yeah.
affect. And the high polarity also will have an impact. It should be moderate rather than.
Moderate.
Definitely. So if it is a low polarity, definitely it might not provide sufficient stabilization to this ionic species. And when it is highly polarized, then that will also lead to certain issues like, yeah, that will like when it is highly polarized, then that also will affect the whole polarization. Excuse me. And yeah, water should not be added. So even though water is polar, it is not advisable to add polar in ionic polymerization because many things will be very sensitive to this presence of water, and like we cannot add water to something directly. Not that will definitely affect the reaction in some way or the other. So the most acceptable answer it should be of moderate polarity. Okay then. So let's move to the next question. That's moderate polarity. So the next question is, during radical change polymerization, the monomer having electrodonating functional group, that is plus R effect, shows polymerization than polymer having withdrawing functional group minus R effect. The statement 2 is like the radical polymerization is not very sensitive towards impurity present inside the reaction, and it also usually does not require catalyst to proceed the reaction faster.
Generally, that first one R effect will not be applicable for radical chain.
Yes.
So I have a doubt with respect to this electron withdrawal or electron addition with respect to radical chain. Whereas the second one definitely, yes, it is not very sensitive
Yes.
to the impurity and does not require a catalyst also, because since the radical free, as long as free radical is available and monomer is available, this will fast go
Yes.
proceed.
Yeah. So that is the thing. So the first one is incorrect, statement one is incorrect, and statement two is correct. Basically, the R effect doesn't play a big role in radical chain polymerization, and the polymerization, radical polymerization is not much sensitive to the impurity as long as it gets this radical, as long as this radical is available, it will just proceed. And also, it does not require any catalyst because the radical itself will propagate the reaction. There is no need of a catalyst to proceed the reaction. Okay, so that's the case. Let's move to next question. For a molecule to have resonance, the molecule must have a conjugate system. Is it true or a false statement?
True.
Yeah, it's very, very true. Okay. Now, yeah, it's a true statement. Now, electron dash functional groups like dash group decreases electron density over carbon-carbon double bond, which result in the development of a partial positive charge over carbon atom, and hence monomers are facilitated by anionic polymerization. Electron withdrawing like, so it should be either donating or function withdrawing like dash. So alkoxy and nitrile. So which one will act as a donating, and which one will act as a withdrawing uh, type. So group decreases the electron density, and then is a general statement. So here also we are talking about a decreasing electron density.
So here, if it is anionic, then it should be donating only electron donating functional groups, and generally it will be alkoxy.
No, I think it is the other way. Since decreases the electron density, so we are basically decreasing the electron density means it is like withdrawing the. It is not donating anything. So it is like decreasing the electron density, right? So it should be withdrawing here, and
Okay, okay, clear.
withdrawing it should be
It's a
inducing.
yeah. Mm. Okay, whether that is correct, decreases the electron density.
Withdrawing would decrease the electron density, right? It's a donor, it will definitely donate its electron, so that will contribute to a higher electron density. So it is withdrawing,
Correct.
then
In cationic case, you need polymerization to occur means you should have a electron donating functional group. But for anionic polymerization, electron withdrawing function group is correct.
yes,
Whether nitrile group is electron withdrawing.
I think that it should be because this was the acceptable answer for the previous, and I have found it very logically also. But exactly that part I don't know.
Okay, okay.
Okay, okay, fine. So that particular explanation part I may not be able to, but from the first part of the question, that is very much logical. Since it electron density is decreasing, it should be a withdrawing, and since it's a withdrawing, it should be an atom. So I found the
So in
logic
that
very
case,
much.
just to yeah, whether
Yes.
the alkoxy is then electron donating.
Hmm?
In that case, alkoxy is electron donating in that case.
Yes. Alkoxy is electron donating, right? Yeah, I think it is electron donating.
Okay, okay,
Yes, it
fine.
is an alkoxy is electron
Because I
donating.
have a doubt
Yeah,
though, because nitrile generally that will have this lone pair, right? Nitrile groups,
yeah,
which means that is ready to donate its electrons
yeah.
readily.
Yeah, it is nitrile, right? Nitrile. The nitrile is
Oh,
electron withdrawing itself. Yeah, this
okay,
is right.
okay,
Yeah, this is a correct answer.
okay, clear, clear.
Okay. The polymer change with unique HT, head to tail placements of functional groups in a chain polymerization is termed as isoregic polymer, cinderoregic polymer, aregic polymer, none. So this is a particular kind of polymer. What do you need? So there is a unique head to tail placements of functional groups. So
Isoregic.
yes, it's isoregic polymers have generally this head to tail placement.
So it is similar to isostatic, symbiotic, and atactic. Right?
Okay, so let's move on to the next question. The fluoride functional phenyl group, polyvinyl fluoride, show different selectivity during radical chain polymerization. This is found due to the absence of significant steric hindrance due to approaching radical and insignificant resonance stabilization. This exception occurs due to small size of fluoride, large size of fluoride, chemoselectivity. None. Regioselectivity means the reaction would happen in a particular region. You will prefer a particular region. This is found due to the absence of significant steric hindrance due to approaching radical and insignificant resonance stabilization. This is an exception due to small size of fluoride, large size of fluoride, chemoselectivity, none.
If there is a steric hindrance, generally that will be large in size, but here we are telling absence of significant steric hindrance.
Yes,
So size will not be big.
yes.
So it should be small size of
Yeah,
fluoride.
it is the small size of fluoride. So, okay. So this one is also from a previous year similar question. So, so do you think the questions are repeating because I don't know this year's questions?
No, but actually, even this particular question, I think I don't know whether we have this particular week lecture, it was there. Uh,
Yeah,
but to confirm, because this actually, like, from understanding only, I just told with respect to steric entrance, but
yeah,
definitely steric entrance part was discussed this time.
yeah.
Okay, okay.
Yeah, this one was from the last year's seventh week lecture.
Anyway, this year it is this assignment, it is not there definitely.
Okay, okay. And I'm asking you in a general question, like are the assignment questions being repeated from like what are like the questions are being asked in the assignments? What are I'm discussing
Yes,
here?
yes. Some questions are little like very few numbers, but it is there in the
Okay,
assignment. It's related
okay,
questions. Yes.
okay, okay. Thank you. Okay then. So let's move on to our next question. So radical chain polymerization is a kind of monomer selective polymerization reaction. Statement 2. Ionic polymerization reactions are relatively faster than radical chain polymer reactions. Choose the correct option. Statement 1 is true, or statement 1 is false. Statement 2 is true, or statement 2 is false.
One, definitely it is not true because already we have discussed it. It is
Mm.
not homo selective.
Yes.
Similar when we compare with ionic.
Mm.
And ionic polymerization reactions are relatively faster. That is also like the free radical is more faster when we see compared to ionic.
So, but actually it is said to be true. Ionic polymerization reactions are relatively faster than radical.
Okay, but here we are having only one option. Either statement one is true or
No,
false.
and statement 2 can be true or false. So which one?
No, here actually the combination of these answers
No, no.
generally.
Here it can be multiple. Choose the correct options. We are asking for options.
Okay, okay, okay. So correct option. In that case, anyway, statement one is false.
Yeah.
Yeah, statement two.
Statement 2 is
But
actually statement 2 is actually true.
okay, okay.
Yeah, that is actually true. So in general, ionic polymerizations is much more faster than radical polymerization, and definitely the monomer selectivity is not a characteristic of radical. It basically depends on the radical that is being found, and then the polymerization continues. Okay, fine. Okay, so these are the questions that I prepared for today. I hope these questions are getting useful for you. So I will try to bring up with these kinds of questions, mostly from referring to the slides and a few questions from the previous year gate questions and then the previous year assignment questions and examination questions. I think how many
Sir,
people?
just one thing.
Yeah, please.
Just can I have a number of Savana, sir?
Number of?
For actually mobile number of Savana, sir. Can I have
I
Savan, sir?
I didn't get you, sir.
Asking Savan, sir. So can I have a number
My number,
like
phone number. Okay.
your or even Savan, sir also? Like
I don't know his number particularly, but I can mail
no,
you my number
I'm
since this will be uploaded
yes, yes,
in
yes.
my
If
Microsoft Teams.
possible,
Yeah,
you
sure.
please.
Yeah, sure. I can
Mm.
email you my number
And
since this
and
is.
and yeah, yeah. And if possible, Savan sir's numbers also.
Yeah, I particularly don't have his number. I have like we two are two independently organizing this. We
Yeah, yeah, yeah,
yeah.
yeah, yeah. I completely understand.
I can
Like,
just email
like
you my
to
number.
actually, I'm going through the lectures. No,
Okay.
so Savan sir also going through the lectures. So,
Okay.
like, if it is possible to like for me and like Savan sir to have a like discussion on if it is like possible
Yeah, definitely
to
you can just
cross check with the answer because very few people are into these lectures. Like only
okay.
me and Savan sir only. I think the only persons who are doing this course.
Yeah,
So it will be helpful
it is
for.
a helpful thing. So
I'm
you can
assuming.
definitely exchange the email IDs.
Yeah,
That would be much more better.
that's what I'm thinking. It will be
Yeah.
nice, like getting in touch.
So if Ronan sir is
Savan
free,
sir,
he can share his email ID in the chat box or something.
No problem here. Actually, I will put it in my email ID because generally phones I will be a bit difficult in office hours, sir.
Yeah.
So I can share the email.
no issue, sir. Whenever like you are like any free, even in my time also, like I'm very like during the office hours, it is very difficult for me to also. I get time at night only,
Mhm.
like after 7 8 p.m. So I generally I will be doing like just for general like in
Yeah, no problem.
case.
Anyway, I posted my email. Hopefully, you would have seen in chat box.
Yeah. So Parthasari sir, you're also
Fine,
working?
fine. Yeah, I'm working in CPET,
Okay.
Central Institute of Petrochemicals Engineering and Technology, as a technical officer.
Okay, okay, sir.
So also pursuing PhD from IIT Roorkee
IT Roorkee.
in
Okay.
the chemical engineering department.
Okay, okay. Nice.
My background is mechanical engineering department, so this chemical reaction engineering thing is very like very new for me, and I'm
Okay.
just trying to cope up with the yeah.
Yeah.
Mhm.
I'm from a physics background and I'm working on batteries.
Yes, yes,
So
exactly. You
yeah.
told. You're
Yeah.
also doing very tremendous work. Very good thing.
Yeah,
And
but
you
the
are also
thing,
this one, na? Pradhan Mantri, that one research, that
yeah,
one, na?
PMR, Prime Minister's
PMRF,
Research.
yeah, yeah,
Yeah.
yeah, yeah, yeah. Very few people get selected on that PMRF. I know
Yeah.
it's very,
Yes.
very good thing.
Okay. Okay, sir. Then, if it is that, then we can wind up for today and I will try to come up with much more better questions in the next class.
Thank
Okay,
you,
thank
thank you.
you
Yeah.
so much.
Okay.
Thank you.
Thank you so much, sir.